NENOMATICA, where mathematics meets YouTube excellence. Welcome to our math video on proving an inequality. Let's start with our example. Given that 0 is less than which is less than 1, and m is less than n where both are integers, we need to prove that a raised to the power m is greater than a raised to the power n. Play button. Let's begin our solution. First, for all m and n in the set of integers, if m is less than n, then we know that n minus m is greater than 0, which implies that n minus m belongs to the set of natural numbers. Counterclockwise arrows button now. Let's look at our initial condition, that 0 is less than which is less than 1. Since 0 is less than which is less than 1, we can raise a to the power of n minus m, and the inequality still holds. So 0 is less than a to the power of n minus m, which is less than 1. Light bulb, let's manipulate this inequality further. We can rewrite the fraction a to the n over a to the m as a to the power of n minus m. So we get 0 is less than a to the n over a to the m, which is less than 1. Thinking face, let's think about this. What happens when we rewrite this fraction? We get 0 is less than a to the n over a to the m, which is less than 1. And also, we know that a to the m is greater than 0 because it is positive. Sparkles now, we can put these facts together. Since 0 is less than a to the n over a to the m, which is less than 1, and a to the m is positive, we can multiply the inequality by a to the m, which gives us 0 is less than a to the n, which is less than a to the m. Therefore, a to the n is less than a to the m, which is equivalent to a to the m is greater than a to the n. And that's exactly what we wanted to prove. We've shown that when 0 is less than which is less than 1, and m is less than n, then a to the power m is greater than a to the power n. Welcome to this mathematics tutorial. Today we'll solve a problem that involves proving an inequality with several variables. Let's examine the problem carefully. The problem is as follows. We have the variables L, C, B, A, which are all positive real numbers, and P times Q is greater than 0. We need to prove the following inequality. N times the sum of a to the power of p plus q, b to the power of p plus q, and so on up to L to the power of p plus q is greater than or equal to the sum of a to the power of p, b to the power of p, and so on, multiplied by the sum of a to the power of q, b to the power of q, and so on. Let's examine some conditions we can derive. If p is greater than 0, then for all a greater than b, a to the power of p is greater than b to the power of p, which implies that a to the power of p minus b to the power of p is greater than 0. Similarly, if p is less than 0, then for all a greater than b, a to the power of p is less than b to the power of p, which implies that a to the power of p minus b to the power of p is less than 0. If q is greater than 0, then for all a greater than b, a to the power of q is greater than b to the power of q, which implies that a to the power of q minus b to the power of q is greater than 0. And if q is less than 0, then for all a greater than b, a to the power of q is less than b to the power of q, which implies that a to the power of q minus b to the power of q is less than 0. Based on the four inequalities above, we can deduce an important property. If p and q have the same sign, meaning either both are positive or both are negative, then for all real numbers greater than b, the product of a to the power of p minus b to the power of p and a to the power of q minus b to the power of q will be greater than or equal to 0. Now, let's expand this product. When we multiply out a to the power of p minus b to the power of p times a to the power of q minus b to the power of q, we get a to the power of p plus q minus a to the power of p times b to the power of q minus b to the power of p times a to the power of q plus b to the power of p plus q. Rearranging, we get a to the power of p plus q plus b to the power of p plus q is greater than or equal to a to the power of p times b to the power of q plus b to the power of p times a to the power of q. We can extend this inequality to include more terms. For instance, we can derive a similar inequality. A to the power of p plus q plus c to the power of p plus q is greater than or equal to a to the power of p times c to the power of q plus c to the power of p times a to the power of q. Following the same logic, we can continue for all pairs of variables in our set of positive real numbers. Now, we're ready to combine all these inequalities. By adding up all these inequalities for the different pairs of variables, we get a sum on the left side that consists of multiple repetitions of each term like a to the power of p plus q. And on the right side, we get products of terms like a to the power of p times b to the power of q plus b to the power of p times a to the power of q. We need to count how many times each term appears on the left side. If we have n variables, each term like a to the power of p plus q appears n minus 1 times in our sum of inequalities. So we can factor out n minus 1 from the left side of our combined inequality. Now, let's look at the right side of our inequality. We can recognize that the terms on the right side are exactly the expansion of the product of the sum of a to the power of p, b to the power of p, and so on, multiplied by the sum of a to the power of q, b to the power of q, and so on. So the right side can be written as the sum of a to the power of p, b to the power of p, and so on, multiplied by the sum of a to the power of q, b to the power of q, and so on. To complete our proof, we add the term a to the power of p plus q plus b to the power of p plus q plus, and so on to both sides of the inequality. By adding this term to both sides, we get n minus 1 times the sum of a to the power of p plus q, b to the power of p plus q, and so on, plus the same sum, is greater than or equal to the product we identified earlier. Combining like terms on the left side, we get n times the sum of a to the power of p plus q, b to the power of p plus q, and so on, is greater than or equal to the product of the sums. As a final note, remember that this inequality holds when p and q have the same sign. If p and q have different signs, the direction of the inequality would be reversed. And with that, we've successfully proven the inequality. N times the sum of a to the power of p plus q, b to the power of p plus q, and so on up to L to the power of p plus q is greater than or equal to the sum of a to the power of p, b to the power of p, and so on, multiplied by the sum of a to the power of q, b to the power of q, and so on. This is a powerful result that applies to many different positive real numbers and exponents. Welcome to our lesson on mathematical inequalities. Today we'll be proving that if a number is between 0 and 1, then a raised to any natural number power n will also be between 0 and 1. Let's look at the problem. We are given that it is greater than 0 and less than 1. We need to prove that a raised to the power of n is also greater than 0 and less than 1 for any natural number n. Let's begin our solution. Step 1. We start with our given inequality. 0 is less than a which is less than 1. Step 2. From 0 less than a less than 1, we can extract that a is less than 1. Step 3. If we multiply both sides of the inequality a less than 1 by a, and since we know it is positive from our original inequality, the direction of the inequality doesn't change. So we get a squared is less than a. Step 4. Now that we have a squared is less than a, and we know a is less than 1 by the transitive property of inequalities, we can combine these results to get a squared is less than 1. Step 5. Using similar reasoning, we can multiply both sides of our inequality a squared less than a by or again. This gives us a cubed is less than a squared. Applying the transitive property again with a squared less than 1, we get a cubed is less than 1. Step 6. We can continue this pattern for any natural number n. Each time, we multiply both sides of the inequality by a, and then use the transitive property to show that a raised to the power n is less than 1. Step 7. Now, let's address the lower bound. From our initial inequality, we know a is greater than 0. Since it is positive, any power of a will also be positive. Therefore, a to the power of n is greater than 0. Step 8. Combining our results from steps 6 and 7, we have proved that if 0 is less than a which is less than 1, then 0 is less than a to the power of n, which is less than 1, for any natural number n. Let's visualize this concept with a graph. We'll plot several powers of a when it equals 0.5. Notice that as the power increases, the value of a to the power of n gets closer to 0, but always remains positive. All the values remain strictly between 0 and 1, confirming our proof. In summary, we have shown that if a number is between 0 and 1, then any natural number power of that number will also be between 0 and 1. For example, if we have 0.5, then 0.5 squared equals 0.25. 0.5 cubed equals 0.125, and so on. The key insight was using the fact that multiplying both sides of an inequality by a positive number preserves the inequality. Welcome to this mathematics lesson. Today we're going to solve an interesting problem about finding a fraction with the smallest possible denominator. Let's look at our problem. We need to find a fraction with the smallest possible denominator that is greater than 1 over 1991 and less than 1 over 1990. Let's solve this step by step. First, let's define the variables. Let's assume our fraction is p over q, where both p and q are natural numbers. Now, we can write our constraints based on the problem statement. We have that our fraction p over q must be greater than 1 over 1991 and less than 1 over 1990. Let's manipulate this inequality. If we flip the fractions and reverse the inequality signs, we get 1990 is less than q over p, which is less than 1991. Next, we'll multiply the entire inequality by p. This gives us 1990p is less than q, which is less than 1991p. Since q must be an integer, and it lies between 1990p and 1991p, we need to find the smallest possible value of p such that there is an integer q satisfying our inequality. Let's try with p equals 2 and see what happens. When p equals 2, we have 1990 times 2, which is 3980 less than q, which is less than 1991 times 2, which is 3982. So q could be 3981, which fits between these values. But we need to check if p equals 1 would work. If p equals 1, we have 1990 less than q, which is less than 1991. There are no integers between 1990 and 1991 and 1991, so p equals 1 doesn't work. Let's double check that p equals 2 is indeed the minimal value. What if p were greater than 2? Then q would have to be greater than 3981, making our fraction p over q have a larger denominator. So p equals 2 is indeed the smallest possible value. Therefore, our final answer is the fraction 2 over 3981, or simplified, 2 over 3981. In summary, we found that the fraction 2 over 3981 is the fraction with the smallest possible denominator that lies between 1 over 1991 and 1 over 1990. To solve this, we transformed the constraint inequalities, found the conditions on p and q, and determined that p equals 2 is the minimal value that gives us an integer solution for q. This method can be applied to find fractions with minimal denominators in any interval. Welcome to this math tutorial. Today, we'll solve a problem involving inequalities where we need to prove that a certain inequality holds true when two variables are constrained by an equation. Let's take a look at our example. We have the equation 2x plus 5y equals 10. And we need to prove that 3xy minus x squared minus y squared is less than 7. Let's solve this step by step following a substitution approach. We'll solve the first equation for y in terms of x, and then substitute this expression into the inequality. First, let's start with our original equation, 2x plus 5y equals 10. We need to solve for y. To isolate y, we'll first subtract 2x from both sides. This gives us 5y equals 10 minus 2x. Then we divide both sides by 5 to find that y equals 10 minus 2x, all over 5. Now, we'll substitute this expression for y into our inequality. Remember, the inequality we need to prove is 3xy minus x squared minus y squared is less than 7. Let's replace y with the expression 10 minus 2x, all over 5. Let's simplify this step by step. First, let's calculate 3x times the expression for y. We have 3x times the fraction 10 minus 2x over 5. This simplifies to 3x times 10 minus 2x, all over 5, which equals 30x minus 6x squared, all divided by 5. Now, let's simplify the y squared term. We have the fraction 10 minus 2x over 5, all squared. When we square this fraction, we get 10 minus 2x, all squared, divided by 25. Expanding the numerator, we get 100 plus 4x squared minus 40x, all divided by 25. Now, let's substitute these simplified expressions back into our inequality. We have 30x minus 6x squared, all over 5, minus x squared, minus 100 plus 4x squared minus 40x, all divided by 25, is less than 7. To make this easier, Let's convert everything to a common denominator of 25. After converting everything to the common denominator of 25, our inequality becomes 150x minus 30x squared minus 25x squared minus 100 plus 40x minus 4x squared, all over 25, is less than 7. Let's multiply both sides by 25 to clear the denominator. This gives us 150x minus 30x squared minus 25x squared minus 100 plus 40x minus 4x squared is less than 175. Now, let's combine like terms on the left side of the inequality. We'll group all the x squared terms together. Negative 30x squared minus 25x squared minus 4x squared equals negative 59x squared. Next, we'll combine the x terms. 150x plus 40x equals 190x. Finally, we have the constant term negative 100. So, our inequality becomes 190x minus 59x squared minus 100 is less than 175. Let's move all terms to the left side of the inequality by subtracting 175 from both sides. This gives us 190x minus 59x squared minus 100 minus 175 is less than 0. Simplifying the left side, we get 190x minus 59x squared minus 275 is less than 0. To make the inequality easier to analyze, let's multiply both sides by negative 1. Remember that when we multiply an inequality by a negative number, we need to reverse the inequality sign. This gives us 59x squared minus 190x plus 275 is greater than 0. Now, we need to analyze this quadratic inequality. We notice that the coefficient of x squared is positive, which means the parabola opens upward. When a parabola opens upward, it is always greater than 0 except possibly between its roots. However, we need to determine if this quadratic expression can ever be less than or equal to 0 for any value of x. To analyze this further, we could find the discriminant of the quadratic expression to see if it has real roots. However, we can skip this step since the coefficient of x squared is positive, which means the parabola opens upward and is always greater than 0 for all values of x, except possibly between its roots. Therefore, the inequality 59x squared minus 190x plus 275 is greater than 0 is true for all values of x. This proves that our original inequality 3xy minus x squared minus y squared is less than 7 is true for all pairs of x, and y that satisfy 2x plus 5, y equals 10. Let's summarize what we've done to prove this inequality. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.